There are two tests of significance in a regression study. Both, though, have to do with the slope estimates, which is B1 right here. So the first one that I discuss here is a test of significance for the entire regression. So again, this is the equation, the regression equation. Typically, when we exclude the error term, we call it the regression equation. Otherwise, with the error term, we call it the regression model. Not such a big deal. Now though, with respect to the entire regression equation, the null hypothesis is that there is no regression relationship. See, because if this coefficient B1 is 0, then 0 times x is 0, and then there's no influence of x, and x has nothing to do with y. So the alternative would be that there is a regression relationship in that B1 is not equal to 0. Alright, so to perform this test, we construct the F-statistic, which is the mean square regression of the mean square error. And earlier I showed you how to calculate both statistics right here. And then at the end of it, based on the degrees of freedom, in this case k is equal to 2, given that we have two parameter estimates here, b0 and b1, we find the f critical value. And then if our calculated f statistic right here exceeds the critical value, which is stationed right at this point, then we reject the null hypothesis and conclude that a relationship exists. So using the earlier data, and if I go back a little bit right here, alright, so this is our earlier data. With this data set, we calculated sum of squares regression and mean square regression, which is 4.9. Also, we calculated, if I go forward, the sum of squares error, and importantly the mean square error, which is 0.3667. So now going back to this presentation, the mean square error, which is 4.9, divided by the mean square regression, which is 4.9, divided by the mean square error as shown, gives us an F statistic of 13.36. So the question is, should we reject or not reject the null hypothesis for the regression? First, we have to look up the critical value. At the 5% level, the degrees of freedom associated with regression, if you recall, is k minus 1, where k is 2. 2 minus 1 is 1. And the degrees of freedom associated with error is 3, which is n minus k. There's n of 5 and k of 2. 5 minus 2 is 3. That's what you see here. So when we go to the F table, under 5%, we look up the critical value. Let's do that. Alright, where do I have it? Right there. Alright, so this is the F table for alpha of 0.05. So 1 degree of freedom in the numerator for regression and 3 degrees of freedom in the denominator for error. And you're looking at the critical value right there, approximately 10.13. And that's what you see right here. Alright? Right here. Alright, 10.13. So as you can see, our calculated F statistic exceeds the critical value in that it lies in here within the significance region. And as a result, we have to reject the null hypothesis of no relationship and conclude that there is evidence of a linear regression relationship between x and y. Now, all of that is summarized in what's called the ANOVA table for the regression. It's analogous to the common analysis of variance table that you learned under the broad topic ANOVA, where you compared the means of 3 or more population. So here, our sources of variation would be explained and unexplained. Explained is on account of regression, and unexplained is error. Degrees of freedom for regression is k minus 1, which k is 2 parameters being estimated b0 and b1. So 2 minus 1 is 1. And for error is n minus 2. N is sample size, and this example 5, and k would always be 2 in a simple linear regression, b0 and b1. And that comes out to be 3. And then total degrees of freedom would be always n minus 1 for the total variation, which is 4. And then we calculated earlier sum of squares regression to be 4.9 and sum of squares error to be 1.1. So that'll make sum of squares total to be the sum of these two numbers, and that's 6. And then the mean square for regression would be sum of squares regression divided by the degrees of freedom. So 4.9 divided by 1 is 4.9. And the mean square for the error would be sum of squares error divided by the degrees of freedom of n minus k. So that's 1.1 divided by 3. That's going to give you this. Calculated F-statistic would be the ratio of these two numbers, 4.9 divided by 0.3667. So that gives us the calculated F-statistic of 13.36. So this is a beautiful summary of the test of significance for a regression. So next up would be test of significance for the slope parameter b1. And again, remember, b1 is the slope. As it turns out, in a simple linear regression, the slope parameter b1 both defines the existence of a relationship as well as a measure of the contribution of x in the prediction of y, in that b1 is the slope of the line and captures the change in y for a given change in x, so that if the slope is 0 or next to nothing, then it means that when x changes, there is no measurable impact on y. So in that respect, the null hypothesis turns out to be exactly the same, that x has no impact on y in the sense that x contributes no information in the prediction of y. So that's our null hypothesis. The alternative would be that that's not the case, in that x does contribute information in the prediction of y. So now, pursuant to that though, we use the t-statistic in this respect, which is the ratio of the calculated b1 coefficient and its standard error, where standard error of b1 is so defined. Now, to find the critical value, it's going to be based on the degrees of freedom, where which is n minus k. And as is customary, we're going to reject the null hypothesis if the t we calculate exceeds the critical value of t. So with that, we're going to use the data we presented earlier to calculate the t-statistic for the slope. And answer to the question, is there evidence that x contributes information in the prediction of y? So the calculated b1 is 0.7, and here I use an alternative notation, beta hat 1, you put a hat on top of it. It's alternative to writing lowercase b1. So these are the two common notations you're going to see in various statistics textbooks. So I just put it here for fun, just to make sure that you have a robust understanding of conventional notation. So whenever you see hat on top, that means estimate. Or if you see lowercase b1, that's estimates as well. Without a hat, that's the parameter, the hypothesized parameter. Anyhow, this is the standard error, and it's given in this problem. So divided into the estimate, we get this calculated t-value of 3.655. So next up is to look up the critical value of t, which under 3 degrees of freedom and 5% level, you'll find it to be 3.182. Again, you can go back to this table which I showed earlier. So as you can see again, the t we calculated exceeds the critical value, and as a result, we reject the null hypothesis and conclude that there is evidence that x contributes information in the prediction of y. In other words, there is evidence that the slope of the regression line is not equal to 0. So now, Here I write a little bit of the implication for the t-test associated with B1. And here I note in particular that B1 is a test. The test for B1 is one that's used to determine whether X has a significant impact on Y, in that X does contribute information in the prediction of Y. So the value of B1 we found in our earlier example measures the change in Y per unit change in X. It is the first derivative. Importantly, in a simple linear regression, if F-statistic is significant, meaning that there is a linear relationship, then the t-statistic would also conclude that B1 is significant, because the two are essentially the same. So what does this tell us? In a simple linear regression, if I go back here, in the case of the F-statistic, if you conclude that the regression is significant in that the F you calculate exceeds the critical value, then you should know right away, even without performing any calculations, that the t-statistic with respect to the slope parameter is also going to be significant, because as you can see again, the statement of hypothesis is the same for the regression as well as, if I go forward, the slope, which is shown right here, even though the two statistics have different distributions. So with F being significant, T would also be significant. And a couple of FYIs right here. If B1, the slope is 0, then that tells us that Y is going to be constant for all values of X. If that's the case, B1 is going to be 0. Also, if X and Y are uncorrelated, then the slope would also be 0, because the one doesn't move the other. And of course, in the context of a regression relationship, if there is no linear relationship between X and Y, then the slope, which is a measure of that relationship, would also be 0. So, and going back to the initial introductory example, if we have this regression equation here where we're trying to capture if a relationship exists between fuel efficiency and the weight of the vehicle, you find that if there is no such relationship, then this slope parameter right here would not amount to a hill of beans. And this concludes this section of the presentation.